Okay.
We're back.
We're back. We're eating jelly beans. Man, how many of those have we had? Look at me.
It's breakfast.
This has been a lot. Yeah. How many calories are in this thing?
I don't want to know.
Yeah.
You're probably going to tell me that, aren't you?
There are. We got 140 calories. If we have finished our 10 servings, we've probably done 4 servings.
At least.
So we were doing a conversion, and we got, where we are, 1 serving equals 140 calories.
That's our conversion factor, right?
That's our conversion factor. And if we got 4 servings, thank you. And we're going to put servings on the bottom and 140 calories up top. Well, that's servings cancel 4 times 140 is
520?
560 calories. We have 560 calories.
Uh-oh.
Split between us.
Uh-oh.
That's counts as our breakfast. Anyway, new podcast. We're talking about energy transformations. Calorie is a unit. Excuse me. That's an energy unit.
One of those things we're going to define and talk about, so make sure you have your notes ready to go.
Okay. If you're GC, this is 6.3.
Central, we're 7.3.
All right, let's do it. 2 definitions we need to start with. Endothermic and exothermic, okay?
But before we even get there,
later.
Let's talk about under the giant umbrella of what that is. Thermochemistry. What do you think of when you think of thermo?
Thermo. I'm thinking of a thermometer.
Okay.
A thermometer, meaning heat. She said thermal underwear last time. Whatever works for you. Thermometer. So this is like heat chemistry. We're studying energies in chemical reactions. So this looks like heat's being released.
Okay. That looks like the factory.
And this looks like heat and light's being released. So
Okay.
these are actually, I'm going to let you know, these are exothermic
Wow.
reactions.
Okay.
And you'll learn. You'll learn.
All right.
And I'm going to learn too. You're going to learn too. So energy. Can I weigh energy? Can I
No, I don't think you can.
You can't. So I can't put energy on a scale. So how do I know that energy takes place?
Well, let's see what the definition is first and see if we can get it from there.
So, first of all, energy is basically you can either supply heat or it's the capacity to do work. And I was kind of trying to trick her. She knows energy doesn't.
There's no mass. You
There's no
can't
mass.
weigh it. You can't measure it with a ruler.
So the only way you can actually observe energy is by seeing what it can do. So we know there is energy. We can't weigh it, but we know there's energy because it can move this ball from the bottom of the hill to the top of the hill. Another definition, there's a couple different types of energy. Chemical potential energy is basically energy that is stored in little tiny bonds.
Right, so a little bit of sugar that are in here that'll give me a sugar high, and then I'm going to crash. It's got chemical potential energy.
So you've heard about a term, energy term before, and we talked about kinetic energy, which is what?
So kinetic energy is the energy of motion.
So this is motion energy. And potential energy is stored energy. So if you want to think of so you have energy stored in those little bonds, and when they break, it releases energy, and you get it, and you go.
Right.
Okay.
Couple more definitions.
Definition heavy right now. So when we're talking about chemical reactions from here on out, we're going to be asking you 2 main questions. What's your system, and what is your surroundings? Now, system.
Right, so the system is the part of the universe that you want to study. This is usually the chemical reaction itself of a physical change.
Yeah, so if we talk about if we have like a little, well, actually I have a beaker on the next side. Okay, so this will help. And then the surroundings is everything else. So if I want to study a reaction in this beaker, my system is going to be what I want to study, which is the beaker here.
And everything else is the surroundings. Now, if you missed that definition on the last slide, please make sure you pause, rewind, and go grab it.
Okay, so we have, this is our system, so I always like to draw boxes around my system.
And I encourage you to draw boxes around everything because it can get kind of hairy with being specific about what system you're studying.
Okay. Law of conservation of energy. I've heard of the law of conservation of mass. Mass cannot be created nor destroyed. If I were to guess,
Energy is kind of the same thing. By kind of, I mean exactly.
Cannot be created nor destroyed. It just changes between stored energy
and kinetic energy.
Kinetic energy, all these different types of energies.
Heat, light, jelly beans.
Yep. So, exothermic, here we are. This is what I wanted to talk about.
Exo. Kind of makes me think of the word exit.
Exit. So this is when energy is exiting or is being released to the surroundings.
So released from the system, so from the little box, out into the great big world, out into the surroundings.
So if I say, here's my beaker, this is supposed to be a beaker, and I'll call that my system, and I'll call all of this my surroundings.
And that's like us watching the beaker, that's the classroom, that's the town.
So energy, let's say this is getting hot, and it's like this guy right here, and fire is coming out. We know that energy is being released. It's going from the system to the surroundings, so energy is exiting. This is going to be an exothermic reaction. Now, what if I called my whole classroom? So now I'm going to do the whole classroom. I'm going to call that my system. Well, now no energy is going in and out the classroom. Let's say I have the door closed, so energy is not exiting or entering.
Nope.
It really depends on what you call your system.
And exiting and entering is not the same as creating or destroying. Just moving.
Yep. So let's go ahead and look at a video clip.
It's hot. Give me a minute. So what's actually happening is I'm not getting colder. I'm letting this heat leave my body.
Okay.
It's the last time I ever jogged.
So it's actually you're not feeling cold air hit you,
No,
but you're feeling
I should use the freezer.
okay.
It's even better.
So you're feeling, but I feel cold. I'm feeling the cold air right now.
So what you're actually feeling is you're feeling that heat from your body leave and go towards the cold air in the freezer.
Right, because cold doesn't flow.
No,
Cold's not a
heat
thing.
goes from hot to cold
So if you're hot, heat is leaving you
and going into the colder
and
freezer.
going into the cold
That's
freezer.
why on a hot day, you run inside and you just sort of stick your face in the freezer.
And it feels good for a while. But overall, we're going to learn that refrigerators, actually what's happening is this isn't going to cool your house.
No.
Because heat is leaving your house.
And going into, we're going to talk about coils that are in here.
It's going into the freezer, and then the heat is,
Going to come right back out, actually, in the coils in the back.
yeah, and if we actually feel back here, I'll let you go back there.
So if you actually go ahead and feel back here, right? Ooh, I don't really want to touch that. But it's actually really warm. And so what's happening is this is an exothermic reaction because the coils and what's in the coils is actually giving heat off. So that's actually going to warm my kitchen or my teacher's lounge up.
Yeah, and so the longer you keep the freezer open, the harder the fridge has to work.
So the hotter it's actually going to get.
Yeah, and so you'll feel good for a while, but the house and the room is
It's going to
actually,
kind of backfire on you.
and that's why fridges are the biggest energy consumer that we.
Just kind of learned a little bit about how a refrigerator works. We have this diagram here, and if you want to follow along with us, we're going to pick a couple different systems and see how energy flows within a refrigerator.
All right. Let's check out those bottles.
Okay, so you put your nice warm bottle in there because she doesn't like to drink warm water, wants to cool it down. So we'll call that our system.
Okay.
This will be our system. And it's hot initially. We all know heat flows from
Hot to cold.
hot to cold.
Never from cold to hot.
So we have heat is going to be removed from this bottle, and heat is going to go into the refrigerator. So that'll make the bottle feel
Colder.
Colder.
Even though it's just really getting less hot.
yeah.
Now everything else is my surroundings, my system, red box.
Okay, an endothermic reaction. This is when energy is absorbed into a system.
So endo, think entering.
Entering. So we have some ice here. And if we just stick ice in a beaker and leave it there, and we leave it in a room, we all know the ice is going to melt, right? And if you were to touch that beaker, it would feel
Cold.
cold. And actually, if you touch that beaker and hold it, it's going to melt faster. Why?
It's going to melt faster because the heat is moving from the surroundings, so from your hand, from the room, into the ice that's in the beaker, so into the system,
Okay,
which
so
is speeding up those molecules.
right. So my hand feels cold when I grab it with 6 fingers. Yeah, 6 fingers. That's right. That's my hand. It feels cold not because it's
Actually cold.
less hot. Heat is leaving my hand, flowing from my hand to the ice, and therefore my hand is getting less hot, and so I feel cold. So less hot basically means it feels cold. And this is endothermic.
Because that heat is flowing from your surroundings into the box that is your system.
So let's say this is my system. Heat is flowing into the system, so it's endothermic. If I picked now let's do my hand. My hand is the system,
And heat is flowing from your hand.
To the ice, this would be exothermic because it would be leaving the system. So it just depends what you define as your system.
Which is why it's so important that you actually go ahead and define those things.
At the very beginning, yeah. Okay, so now pick me a new system.
Let's try those evaporating coils.
Okay, so this will be my system now. And what we've got here is in the beginning, we've got cold, super high pressure liquid. Cold, super high pressure liquid, and it's a coolant. And it goes in your refrigerator, and since it's so much colder in here, or less hot, really, it's less hot, and the bottle and everything else out here is hotter, heat is going to flow from out here into the coils. And when it does that, this is going to make your food cold, and it's going to make the coils hot. So the coils are drawing heat from your food. So the liquid or the coolant heats up.
And this is experiencing an endothermic change.
And it's an endothermic because heat is entering the reaction. So heat is entering the system. So this is an endothermic.
Now let's look at it as a whole. Right, so what if we thought about the entire refrigerator in your kitchen?
Okay, so if we talked about the entire refrigerator, well, if we drew and made this whole thing the system, we already know that when we felt the back of the fridge, it felt hot, right? And so heat was being released by these coils, and since heat is exiting my new system, what type of reaction?
Exo.
That would be exo, which is exothermic. So heat is exiting. And just real briefly, just want to tell you how a refrigerator works because this is kind of cool. You have your super cold liquid. It draws heat away from your food, and then when it draws heat, liquid goes to a higher energy state, and it turns into
gas.
Turns into a gas. So now we've got a gas going here, and then we use it, put it back into a compressor, and that compressor compresses that gas into a liquid, and it becomes a hot liquid, and then that's what's running through these coils out here and releasing that heat.
Exactly. So.
Before we move on, we need to tell the difference between heat and temperature, because people mix this up all the time. So I was actually getting mixed up too, and so was Miss Morris. So we'll do our best here. What do we got here on the left?
Looks like we have Warrior River.
This is actually the Warrior River, which is a big body of water. And then we've got hot cup of coffee. She's got a hot cup of coffee right here. So if I were to ask you which one has more heat, the coffee or Warrior River, what would you say?
My coffee.
Your coffee. And actually, it's not that you're wrong. It's just like me, you're a little bit confused about the definition. You're probably like all of us, so let's figure this out. It has a higher temperature, but it has less heat.
Okay.
Okay, so go with me on this. Go ahead and draw a T-chart of what heat and temperature. So temperature is actually defined as the average kinetic energy.
Remember, kinetic energy is the energy of motion.
Of a liquid or a gas, whatever it is. Average of
something.
Yeah, so the solution or liquid gas, whatever. So you probably remember from a
previous podcast,
we had this diagram here, and it was called the Boltzmann Diagram. And we had on the right, we had number of molecules, and we were measuring the speed of all those molecules. And we said the average speed was right at this peak. And, well, the average speed, or the average kinetic energy, this is defined as my temperature.
Okay.
So this has a very specific temperature because that's the average kinetic energy. However, heat deals with all of the energy, not the average energy.
So how does that Boltzmann diagram work?
So if we draw the same diagram, it's the same one, all the energy in the system is measured by all of the molecules.
So instead of having just one point, it's every molecule underneath it.
All of it. So heat is defined as all of the energy, while temperature is defined as just whatever the average is.
Gotcha.
So good way to look at this is this actually has more heat.
Okay.
Okay? Even though it feels colder, it has more heat because it's a bigger body of water. So there's a lot more energy in the Warrior River than your cup of coffee. But, so this is more heat, lower temperature. Obviously, we know that because the average energy is lower. This would have less heat, but a higher temperature.
Okay.
So how can I remember this? How can we relate?
Let's see. It's springtime, so it's almost baseball season.
Almost, April 1st.
Okay,
Opening
good to
day.
know.
I'm excited.
April Fool's Day.
Taking the day off.
Oh, well, no.
Yeah. National holiday. So where are you going with that?
So I'm thinking about crowd and the crowds at the baseball games.
Okay.
Right? So I'm going to have a baseball team that has a lot of fans.
Okay, so I've got so I've got my stadium, and here are my bleachers, and it's got all these guys, and they're all ton of fans, right?
So they all show up, but they're all just like, woo, baseball. Right? Not a lot of energy going on there, but there's a lot of them.
Like, I kind of like this.
It's springtime. I'll watch it.
Okay. And where else are you going?
And then I'm thinking of a baseball team that has just a few die-hard fans.
Yeah, it's like they suck. The team sucks, but you know.
But I'm just going to give it my all and going to lose my voice because I went and I saw that baseball game.
So we've got just a couple guys
with a lot of energy.
A lot of energy. So their average energy is really
high.
Just because there's two of them. On average, they have a high energy. So this would be like my high or hot temperature.
Mm-hmm.
But we have a lot of people over here with a little bit of energy.
Yeah.
If we add up all their energies, they definitely outnumber the amount of energy these two guys put. So they have more heat, but on average,
they have a lower temperature.
Lower energy, so they have they would feel lower temperature. So these guys, super high temperature, but since there's only two of them, they're a low heat. Because if we add up all the energies. Okay. So how does this factor into what we've been doing? How does it connect to stoichiometry and chemical reactions?
So let's talk about exothermic. Remember, exothermic is it's exiting. We're just going to go ahead and see it on our product side. So that is our right side of our equation.
So we have reactants. We have methane combusting. And how do I know this is a combustion reaction real quick?
So I've got some oxygen, some carbon dioxide, some water, and I'm going to get some heat eventually.
Yeah, so it's going to release heat. This is an exothermic reaction, so it's on the product side. And this is how we call it. This is called change in heat. This means change in.
And so what's up with that negative sign?
Okay. This negative is going to be very important. The negative or the positive is going to tell you what side to put the energy on. So I know just from, running a car and combusting that energy is being released, and that's what allows my car to move. So I know energy is being released, it's on the product. But if I didn't know that, I could look up the reaction and I could find the heat of reaction, which is measured in joules per mole, energy per mole.
And that K is a kilojoule.
Yeah, kilojoule. And this negative is going to tell me, well, heat is going from the system to the surroundings, so it is exiting, so it's going to be called negative. So we're going to take that energy and we're going to put it on the product side.
Okay. Now when we actually go ahead and put it on the product side, check out, it's a positive.
Yeah, so we're going to add the energy after you figure out what side it goes on. Oh, negative, it goes on the right side. So negative, maybe add that. Right side means a negative delta H. Once it's negative, I figure out which side it goes on, I forget it. Then I don't worry about it, and then I just put it whatever side it is.
So it's always positives in the reaction.
Okay, go ahead and draw this diagram in your notes. We're going to be working with these and practicing with these a lot.
So this is an energy diagram specifically of an exothermic reaction.
So we've got the start of the reaction here, and we've got the end of the reaction here. So at the start we've got our reactants, and then we've got our products. Now imagine you're going to take these reactants and you're going to push them up this hill. Well, in order to push them up the hill,
it's going to take some energy.
So you can see the amount of energy that it's going to take to move up that hill is a certain height, and that is called the activation energy.
Okay.
That is the amount of energy that we have to put forth in order to activate this reaction.
Okay. But then once I get over that activation energy and I hit that really tippy top of that hill, I'm good to go.
Yeah, it doesn't take any more energy to go down and move down this hill.
Now let's check out that y-axis.
Okay.
It's got energy increasing. So my reactants are at a higher energy than my products are.
Yes, so let's look at that. If we were to measure across, yep, you can see the reactants are indeed on a higher stair than the products.
So they've lost energy, which makes sense with the exothermic because the exothermic energy has been released.
Yeah, so at the start, higher energy, at the end, lower energy. So energy was lost, which means so my delta H, my delta heat is going to be what?
Negative.
It's going to be negative because energy was being released or was exiting the system. And an endothermic reaction.
Right.
Just the opposite. Energy is going to go on the left side of your equation. So we've got ammonia decomposing, because it's starting with 1 and ending with 2, into hydrogen gas and nitrogen gas, both Brinkelhoff gases. Okay. So what is the sign here?
It's positive.
It's positive, right? So negative went on the right side. Positive must mean it goes on the
Left side, or my reactant side.
left side. And remember, the sign tells you which side of the equation to write the energy on. So energy is going to go on the left side. Okay.
Energy diagram of an endothermic reaction. Look, you still have energy on the y-axis.
Yes, this is endothermic. Yep, and we've got the start of the reaction, or the initial, and the end of the reaction, or the final. Okay, so we got our ball. Going to take some energy to push it up that hill. What's that energy equal to?
That is your activation energy.
Yeah, so this height, that is my activation energy. That's how much energy I got to put in. Okay, and once I get up to this hill, it is pretty easy for it to go down. But whoa, it doesn't go all the way down.
No, so your products are at a higher energy than your reactants.
Yeah, so the change in heat overall is positive. So if I did the final, let's say this heat value is like 20 kilojoules, and this is 5 kilojoules. I'm going to do the change in heat is going to be 20,
which is your final,
minus my initial,
which is 5.
5. So overall, this is a positive
15.
15.
So that means that 15 kilojoules had to be added from your surroundings into that system for that reaction to happen.
And that's why when we write our equation, like we did in the previous one, we have NH3. Well, we can just go to it. We have NH3, and we got to add that energy to the NH3 to decompose it and make our products.
And we're going to talk about exactly how you find that number. So instead of writing general energy, we know it is exactly 76.7 kilojoules per mole.
We're going to be able to calculate that, and we're going to be able to say, hey, I got 10 grams of ammonia.
And
yeah.
we're going to tell you exactly how many calories and kilojoules are in these jelly beans.